Researchers have demonstrated that stretching shape memory polymers embedded with clusters of gold nanoparticles alters their plasmon coupling, giving rise to desirable optical properties. One potential application for the material is a sensor that relies on optical properties to track an object or environment's thermal history. At issue is a stretchable polymer embedded with gold nanospheres. If the material is heated and stretched, followed by cooling to room temperature, the material will hold its stretched shape indefinitely. Once reheated to 120 degrees Celsius, the material returns to its original shape. But what's really interesting is that the gold nanospheres are not perfectly dispersed in the polymer. Instead, they form clusters, in which their surface plasmon resonances are coupled. These plasmon-coupled nanoparticles have optical properties that shift depending on how close they are to each other, which changes when stretching alters the shape of the composite. When assessing the peak wavelength of light absorbed by the material, there are significant differences depending on whether the light is polarized parallel or perpendicular to the stretching direction, says Joe Tracy, corresponding author of a paper on the work and a professor of materials SCI. For light polarized perpendicular to the stretching direction there is a blue shift. We also found that, while the shape memory polymer holds its shape at room temperature, it recovers its original shape in a predictable way, depending on the temperature it is exposed to, says Tobias Kraus, Co. Specifically, once stretched 140% past its original length, you can determine the highest temperature to which the polymer is then exposed, up to 120 degrees Celsius, by measuring how much it has shrunk back toward its original size. What's more, because of the plasmon-coupled nanoparticles, this change can be measured indirectly, through measurements of the material's optical properties. An important application of thermal history sensors is assuring the quality or safety of shipping or storing materials that are sensitive to significant changes in heat. We have demonstrated an approach based on plasmon coupling of gold nanoparticles. The sensor concept was developed empirically, but the researchers also used computational modeling to better understand the structure of the clusters of gold nanospheres and how the clusters change during stretchy. The strength of plasmon coupling is related to the spacings between nanospheres, which is known as a plasmon ruler. Based on our simulations, original written by Matt Shipman. Note: content may be edited for style and length. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.